What if you could predict fatigue life using just one simple mechanical test? In this video, I'll show you how to estimate fatigue life by combining Abaqus and FE-Safe using nothing more than a tensile test sample. I'll walk you through the full workflow from running the simulation in Abaqus to importing the results into FE-Safe and predicting fatigue life step by step. No unnecessary theory, no extra testing, just a practical method that actually works. Let's get started. Now you learned how to create model and perform fatigue analysis in stress-based mode. Let's solve more examples with different materials, different loadings to have a better understanding of this topic. Today I chose a tensile test sample. This is created based on ASTM E8 standard, and as you see here, this is the section, 100 millimeters in length, while the gauge length is 25 millimeters. This time, unlike the previous examples, we have different materials. So the material today is aluminum alloy. This is the density, 2.7 E-9, while it was 7.8 for the steel, and the elastic modulus is 70,000, while in the steel it was 210,000. The Poisson's ratio is the same. Okay, let's go and check other parts. The step is a static general 1, and these are the details. If we go to the interaction, we have a reference point here, and it is coupled to this region. And if we go to the load, the first loading condition we have is to fully fix this part and let this part to only displace 0.1 millimeter in the Y direction. We don't need the amplitude here because we're going to apply the amplitude in the software. And let's go to see the mesh. This is the mesh we have, but this time instead of a full analysis, we know that we only have the stress in this region. So I created a set number 7. Let's rename it to gauge length. Okay, we have this one here. We're going to perform the analysis only in this region. I tell you why. So let's go to look at the job. Here, as you see, we only have the stress here. So if we want to include this part, we're going to increase the cost of the analysis just for nothing, as we know we have all the stress here. Okay, let's plot the force versus displacement from ODB field output. We go continue. This is why we have the reference point here, reaction force 2, RF2 and U2. And here from node set we can have the reference point, and if we plot that, it's easier for us. And if we go to the XY data once more, operate on XY data, continue, we have combine here, double click it on this one, U2 and RF2, and if we plot that, you see here we have the force versus displacement, and as you see it's linear. We are in the elastic region. We don't want to go to the plastic region. You think it might be in the plastic region, but it didn't surpass that much, so we're kinda in the elastic and plastic region, which is called elastoplastic region. So now it's time to go to FE-Safe to see the model. Okay, now we open the FE-Safe. Let's rename this one as tensile test and create. Okay, let's open the finite element model. Now I have to find the model. Here is the tensile test. Let's open it. Yes. We don't want temperature, we don't want initial orientation and others. We only want a stress in the last increment. And if we hit OK, because by default it selected other things, it asks us to make the changes. As you see, we only have the stress here. Hit the OK button. This should be megapascal, strain, degree centigrade, Newton, and millimeter. OK. Yes. Now we only need the gauge length. So this is the set 7. I forgot to submit the job after. Doesn't matter. So we set everything to this side. As you see, we have 1800 elements in the model, but in the set 7 we only have 700 elements, so it's more efficient, especially when it comes to complex models. Okay, now we need to hit the edit, do not analyze, and double click on this one, whole group, and the algorithm must be, let's select uniaxial stress. We can have Goodman, and OK. Now we have to find the aluminum alloy from system. Here we have, let's say, this one, aluminum 224 T4. It says the constant amplitude is this one, the elastic modulus kind of the same. Let's find another one. To see this one, the elastic modulus is higher, this one is a little lower, this guy is also a little lower. Yeah, let's stick to the first one, which is nearly the same, and the Poisson's ratio is also the same. So this one, double click, and yes, now we have the materials assigned. But in the loading setting, this time, first I want to clear all the loadings. Instead of creating the signal generation here, I want to add a user-defined load dataset. So if I go here and select this one and add a user-defined load set and click on OK, here I can use the load scaling. For instance, 1 and -1. It means we have a fully reversed load. Let's hit on OK button, and we're good to do the analysis. Continue, and as you see here, we have 140,000 for this one. Let's check if we clear this loading and we generate a signal wave here. Let's put this guy on 4, 1, 4, and assign the amplitude. Okay, we have this one. Let's plot it. Yeah, this is the fully reversed one. This goes to 1 and -1. If we select this one, add load dataset, and okay, let's do the analysis once more. Let's see if we get same number or not. Yeah, as you see, we got the same number. So this method is way more easier to just clear everything at first, then add a user-defined load dataset. So I click on OK. Here, now we can have the loading we wanted, 1 and -1. Okay, I want to hold this here, and let's go and see the job first. Okay, I want to change the output to different place, such as temp. I can create a new folder here, and tensile test. Yeah, results can be here. I want to analyze this job once more. Continue and open the result folder. Here I can see the results. This is the results. Okay, open it. Okay, as you see here, we don't have any colorful contour. It means it's not in the analysis, and we only have this part. Let's unify that with Abaqus. So if we go to the spectrum and reverse the rainbow and click on OK, you see here in this part we have the lowest life, and it is 5.15. To extract that more accurately, we have to go to the tools and query and probe values. I can put this on nodes, and for instance we can have it somewhere around here. It shows the value. Now in this kernel I can have 10 to the power of 5.22795, and it gives me 169,000 for this node. But we have different nodes here. For instance, here is 5.16. It means it's more critical. So 10 to the power of 5.16 to 55, and it's 145,000. So using the probe values, you can use wherever you want and analyze it more carefully. Okay, now let's go and see what would happen if we change the load. So this is 1 and -1, and if I put this one on 0 and 1 and on hit OK, so in this one I said Goodman 01 for instance, and I can do the analysis. Okay, continue, and as you see the life increased to 5 million cycles. Let's see the results here. So we have the Goodman, tensile Goodman ODB file. Let's see spectrum and reversed rainbow. And as you see, the contour, even the contour is different. It means the loading does really matter, because in the fully reverse load we have tension and compression all the time, but in this one we only have tension. So by changing a loading condition, you can increase the life of the component. So here you see only in this part we have the lowest life, which is 10 to the power of 6 is like 5 million, and with excluding this part we could run the simulation faster. You might not see that much difference, but if the component is complex you would see a huge reduction in time. And that's it. If you want to learn FE-Safe more thoroughly, click on the video on screen and I see you there.